You are able to see the screen, right?
Sir.
No. Okay. More thing also. No, yes. No. So you are able to see, right, this screen, the geological map of India. You are able to see.
Sir.
No. So anyway, so as already last class, we have discussed about all the geological timelines and so many things we have discussed. Okay, so this is very important, in planetary geology or even in the planetary explorations. Okay, so like this, I showed you, quaternary era, tertiary era, all those details we have seen, and we have said that this Archean is the oldest one. So this is a geological map of India, which I showed you last class, arranged in terms of the ages of all the sediments. Okay, so this is the most important thing. So now tomorrow when you are sending a planetary missions, say, like for example, if you take India, okay, so let us say, where do you want to land? So suppose if you want to decide the landing site, say, so where do you land this one, So how do you decide the landing site here? So on what basis or what is advantages, like which is the best landing site, Suppose if you take India, so which is the best landing site here? How do we decide? See, suppose if we land this place, say, what is that you will get? No.
That is the youngest format.
Yeah. So this is the youngest format. Suppose, so this is the most important thing. So if suppose, if you are designing to send any rover or whatever, say, if you want to know about the youngest things or the recent changes, what has happened on that particular planet, so you can land it here. Suppose if you want to know the history, say, like, you want to know the oldest history or whatever, then where you have to send the rovers? No.
To the south side of India.
To the south side, basically. So that's what I'm trying, the geological things, becomes very important, in deciding the landing site and others. So that's why, this course and the planetary geology becomes very important. So this ages, say, at least if what is the geological age of that planet, say. So before sending the rover, you can take decisions, and then, the pros and cons and other things can be done. Okay. So this is the most important thing. So now anyway, Earth is very simple, so we have already seen Hadean, all those things, so we have all the, this one also. But here for the Earth, say, so now the most important thing, what happens is, we have all the details. So all the geological boundaries, which I showed in the last class, say. So what are these boundaries corresponds to? See, like for example, Archean era. Okay, so these are all the boundaries. So what do they physically? What's the physical significance of all these geological boundaries? Last class, what did we say? See, what does they indicate? Like you say, Archean era, Proterozoic era, say. So we have said, right? So this boundary line, say. What is the meaning of this boundary line? No.
Significant geological events are taken.
So what happens is Archean era, we said, right? Like Hadean era. So Hadean means what we said was the whole Earth, there was no rock at all. Everything was in a molten kind of a state. So this boundary from Hadean to Archean era starts. That means you see something geological, like rocks have started forming. So all these geological boundaries, so they have a very significance, like the important events basically, which have happened on planet Earth. Okay, so this is what the geological time scale looks like. Now the question was, how do we find out this on other planets? Okay, that is for Moon or for Mars or something like that. So now it is very difficult, because Moon and Mars, we don't know, because our geological time scales and the boundaries have been drawn based on this, photosynthesis or life or whatever, dinosaur extensions, or so many things have come up. But if you see other planets, it is extremely difficult. How do we find out this geological boundaries? So what one does here is that for other planets, to say, now how to the, so the only way, that is this geological boundaries. So like for example, if you see Moon, say, they have divided into pre-Nectarian, Nectarian, Imbrium, Erastasian, Copernican kind of thing. So they have divided. So all these things comes from the impact cratering only. So like what people have done is, all the impact craters, say, so they have found out on Moon, and then they have done the carbon dating. Of course, human missions went there. So they have done the carbon dating, and then based on that, once approximately they have divided Moon also into some, 4 boundaries or 5 boundaries. or something like, and this is a tentative. But moon, at least we have some samples, brought from Apollo missions. So approximately, they are fine. So you can divide the moons into some 4 or 5. So these are the boundaries basically. Okay, so some major things are, something have happened on the moon itself. Now, if you take other planets, say Mars, Venus, of course, Mars is very difficult because it has an atmosphere also. So the craters may get eroded actually. Okay, so this becomes an issue. So how to find out this geological time scales? So how do we do this for other planets is the question. Okay, so this is what we are going to discuss. Yeah. Yeah. So now on Earth, as already I told you, the geological boundaries has been decided based on planetology, rock formation. So many things are there. But now, how do we do this for other planets itself? So the most important thing, what now it has understood is, how a planet gets formed. Long back, I told you, right? What is the how planets gets formed? What is the basic thing for to form a planet? What mechanism happens? See, the starting classes I told you how planet gets formed, like Earth or whatever planets, how it forms. See, what is the methodology? Long back we discussed, right? So how does a planet forms? So in the starting lectures, I told you, right, that inventory or whatever we discussed, how a planet forms, like you remember, how a solar system forms, the dense molecular cloud, and then you followed. So what is the basic mechanism for a planet? How it forms? See, all of you remember that one, how a planet gets formed, So if you see the older slides which I have shared you also, how solar system, how planet forms, as already I told you, right? From the dense molecular clouds, so sun will get at the center, and the remaining particles, what happens? They impact each other. You followed. So like that, you see the planet gets formed. So what is the most important thing for a planet, or what is the most important mechanism, or what most important physical the process to form a planet is basically, yeah. So most important thing is. Can you read this statement, this word here? Now, what is this here? So the most important thing is
Impact craters.
Impact craters. Okay. So generally, planets, all the planets are formed due to impacts only. One asteroid, all small particles, they impact one another, and then the planet gets formed. After that, also, of course, we will be having a lot of impacts. So now the impact cratering, say, now in planetary geology, so now everybody has accepted that important impact craters is the starting essence, actually. The entire, the formation of planet, the cratering only. So now what they say is, now suppose there will be a large amount of craters. Even on Earth also we had so many craters was there, but Earth is very atmosphere is there, plate tectonics is there. So many all the old cratering surfaces have got eroded actually on Earth itself. But if you see moons, since there is no atmosphere, so what happens is so the old surfaces actually have been exposed to the impact environment for long compared to younger surfaces. So obviously and statistically should contain more impact craters. So based on that say we can decide the age of or geological age of these craters also. So now what one does is to find out those geological boundaries, we count basically the number of craters. So you go to moon, say you select any region, say in that region if you want to find out the geological age, so you count how many craters are there and others, so based on that size frequency distribution, we can find out the age, relative age only. Okay, but if you want to have absolute age, say, then you have to do carbon dating and others itself. So relative ages can be found out, like whether this is old or that is young. You remember that Steno's laws also we discussed long back. So this methodology people use to find out for other planets also. So this concept, say, it was developed first. It was developed for Moon, and then there was a chance actually whether this is correct or not. So Apollo missions went. They brought the rocks from those crater regions, and then when they did the carbon datings, it exactly matched with this crater counting methodology also. Okay. So so these are the number of craters on moon. Okay, so I'm just showing you here. So if you download that moon's topography data, as yesterday Meenakshi has sent you the link, and if you open in that QGIS, you can easily count the number of craters. So this is a whole craters, say whatever there on the moon, this is how it looks like. And then these are the craters, say, and then you find out their ages based on the crater frequency distributions. So it looks like this. So all the craters, the red color which I'm showing you here, so these are all the age of these craters is different basically. Now age of these other craters, so it is different, like this, 1, 2, 3, 4, 5. So 5 the ages have been found out. So which say that so on moon, say, so you will have these 5 geological boundaries itself. So this crater counting procedure, say, is the one which now everybody is using for finding the geological ages, that are essentially the relative ages of these places on the other planets itself. So this is what it says. So this was one famous, so this person say, okay, so this Gould, basically, the Don Gould from NASA. So he was the first person, who started this thing, and who is a crater frequency, like for estimating the ages. This NASA scientist he showed, the planetologist, So what he says is like this. Basically, he has done a lot of experiments. His entire report is available in Google. You can download and you can see also. He has done a lot of experiments. So what they say is like this. So he has done some experiments. So this is one surface he has taken. Okay. So there are no craters. Then after that, he has impacted with some, projectiles or whatever here. So as a time passes away, so many projectiles have been done. So now this is the final one itself. So what he says is that the age is very young. Say. So this is something like the youngest, the surface itself, and where you will see a large number of craters. That means its age will be very old basically. So you can see. So here the last row of the photographs, the crater are here. So he has done a lot of experiments. So these are the youngest ones, the first one, the next one, like that, it comes. So if you see more number of craters, the density is very high. That means it is a old surface, and if the density is very low, that means it is basically a new surface kind of thing itself. And based on this, you can do this, the ages of this one also. So this is also another thing I'm showing. So, but there are some difficulties in this methodology. Like this is a new crater which has been formed. So generally impacts are keep on happening basically. So what may happen is after some point of time, so due to additional cratering after some point of a time, this crater may get eroded also. You can see this was the original figure. After doing so many impacts, finally this crater has disappeared also. So this also happens here. So what he did was, this moon was, they took all the craters basically. Okay, so these are all the craters, whatever they have collected on all the moon data. And then they found out, like they divide this into regions, some small per square kilometer, like 20 by 20 kilometers square or something like that. And then they used to count the number of craters in that region. And then they used to find out, the density. So if you plot a cumulative number, you count all of them and then divide by the area, say. So you will get how many number of craters per unit area you get, and then you plot them as a function of the crater diameter, so you get these type of lines itself. So this thing he has got from the experiments. And then what he says is there will be some equilibrium will be there. So now the region, say, where you will see more number of craters basically. So if you see surface 1, surface 2, surface 3, so this is a crater density. So where the crater density is high now. So if you see here, say, which is the oldest one, which is where crater density is very high, on surface 1 or surface 2 or surface 3. So if you compare these three, say, suppose if I take crater diameter 3, okay. So this crater diameter 3, say, so where the density is very high, on first surface or second surface or third surface. Suppose if you take crater diameter 3, and if you find out this is the density, say, on which surface it is more?
First one.
First one. So that means surface 1 has large number of craters basically. So if the surface is having large number of craters, say, what will be the age of that one? So more number of craters, like in this graph also, here if you see more number of craters, what does it mean? No. More number of craters means that surface has been exposed for? No.
It's older, sir.
No, it is older basically, followed. Suppose if you see young, this surface is, so you will not see much more craters itself. Okay, so that is how they find out this relative ages of all these regions also. So this is a technique, people, of course, we will discuss the mathematical aspects also for some point of a time. So this is a technique, which people use to find out this, to find out the relative age of a particular region. So the main advantage is if I know the age of all these regions, say, so when you are sending a rover or when you are trying to decide a landing site, so you can decide, you follow it. So where, which is the youngest region, which is the largest region, you follow it. So that is also becomes very, very important actually. Now, apart from that also, the crater counting is very important even for landing. See, suppose if you're having a crater, say, small crater is there, you have to detect from the images also. And then if you land a rover on the craters, and if the crater size is very small, see, craters are all, like a circular bowl kind of a thing. So if you land a crater in a bowl, say, what happens? So if you have sent a rover, say, and finally it has landed in a small crater of size, 100 meters or 200-meter crater size, the rover has landed inside it. So what's the problem you see? Yeah. See, crater is a circular bowl kind of thing, the perfect circular or maybe ellipse kind of thing. And if you land a rover in the crater, say, what happens? Yeah. What happens to its movements?
So mobility will be difficult.
Yeah, so it cannot climb, you follow, right, the rovers, because you have to have more charge, so that also matters a lot. Suppose if you land your rover in a huge crater or maybe a perfect flat this regions, then the rover can travel up to large distances and it may able to get more amount of data, and then lot of samples also can be analyzed. So this crater business is not only for finding the geological ages, but at the same point of a time, it is also used to find out, where to land a rover such that it will not be located in a small crater. Mobility will be a issue also. And then how do we find out the craters? How to detect the craters from a given map? So that is also a very important, challenging task. One is manually you take a figure and then you count manually itself. But then when you're doing it at planetary scales, it becomes very difficult. So now to identify the craters, like this type of map will be provided to you, the topography map of moon. So from that map, you have to find out, you have to detect all the crater boundaries are this one. So nowadays, I have picked up from a paper, see, where they are using machine learning tools, So like once you given an image, it's a topographical image of any planet, you see. So people are trying to develop manually anyway, you can count also, but now, machine learning, other techniques they are using to detect the craters itself. Once the craters have been detected, say, then you can find out the age and the frequency and other details also. So this is the one philosophy which has been used to find out relative age of the regions on other planet itself. Okay, so that's what we said. So in practice, so when you do these issues a crater, that is perfectly fine. So now what happens is we are going only by impact craters, but at the same point of a time you can have a volcanic process also. See, in the olden days, what people said was on moon, they said that these type of craters are formed not due to impacts. I told you, right, long time people used to do this volcano kind of a thing. Okay, because what happened was the craters are perfect circular, say. So the crater is a perfect circular. What happens? So if it is perfect circular, people used to question, because if you have because the craters will be inclined, because of the gravity or whatever. These are not like inclined; they should be strike just at 90 degrees. So people said this type of perfect circular things can happen only due to volcanic things. Impact craters, it will not be perfect. There was some arguments was there, but now it has been removed, and impact craters, that has been accepted. But sometimes what happens is these type of craters, they get formed by volcanic process also. So if you mix the volcano craters with impact craters, then you will have some kind of a bias, or some other issues will come up also. And of course, the volcanics, there are so many volcanic craters are there, so then the surface would appear very old also. This is also a big challenge. Then apart from that, in addition, say, secondary craters, they get formed by the impacts of rocks ejected from the primary impact craters itself. So like for example, when this crater was formed, say, when this impact happens, what does it do? Suppose a projectile strikes at this place, say. So this with the ejecta, that is, some material will fly off actually. Okay, something like last time also I showed you in lunar crater, that ejecta blanket or something like that. So the small things, they just fly off from this place and then they fall on the other surfaces, and they also will create some type of small craters basically. So these craters are not from the direct asteroid impact or something like that, but they have been created by the first crater formation, say, some material getting ejected outside and it clicks, and then so it also creates these kinds of impacts also. So this is also very important thing, that the difficult. So when you try to count the craters, So the primary impact crater, you are saying you will take this also as another independent crater and you try to count it also. This also is a very important thing, in the challenge basically when you do this crater counting process. Then so that's what we, so the secondary craters is if it adds to the total crater population, and then it appears as though the age is older, but this may be a younger also. Okay, so how many secondary craters, how do you remove this one? So this also becomes important. So one is volcanic, another one is secondary, this one. And of course that's what you see, these type of models all the people are using, but secondary craters it's very difficult to remove, and then other things also. Then other considerations say include a target that could cause variations in the crater sizes. So the crater sizes also may be different also. So like for example, say if the crater forms in a a region say which contains a fluid, or it may be a soft soil or something like that, then the crater diameter may be high. So although the projectiles which is hitting doing the impact, although the projectile size is same, say like 10-meter impactor size, say if it falls on soil or some soft kind of material, the crater diameter will be more. But if the same thing happens on a hard rock kind of a surface, the crater diameter may be less also. So this also is a big headache actually, the crater diameter. So if it is a soft soil, crater diameter will be high, although the impactor size is same. But if it is in a hard rock, say, then the crater diameter may be small for the same size of the impact itself. So this also creates some kind of a bias actually, the crater counting processes. So that's what is. So that's differences. So what happens is the old surface may be interpreted as young surface, or young surface may be interpreted as a older surface. So these are some issues basically. So volcanic crater is a big issue. Secondary craters are also another challenge. How do we remove the secondary craters? And then the third one is the crater sizes, the diameter also. If it is on soft soil, what will happen? If it is on rock, what will be the crater diameter? So this also we have a lot of problems. So then so by although we have a problems, but people have now recently developed a lot of techniques, by mathematical techniques. They have done a lot of experiments also, and then we will discuss after some point of a time. So this crater counts, you can even also find out the absolute age also. You follow not only the relative age, absolute age also one can find out from this crater counting process. So this is a graph, we will discuss the mathematical aspects after this one. You can see here. So this is Apollo 16 landing site, 14 landing site. So they have these type of graphs also. This is a Copernicus crater, Tycho crater is here. Now you can see time before present is in the x-axis. So they have done from the crater counting process, and then they have even validated with the radiometric, radioactive dating also. So you can see the typical highlands is on Moon. They are very old, the places. And if you see the Copernicus crater, Tycho crater, say it is a very young the crater itself. So this crater counting can be used to find out the absolute ages of this one also. Okay. And now the only thing is for Moon it has been very well established and very well calibrated, but Mars and others still we don't have like some solid evidences basically. Okay, so this is what so the lunar cratering says. So this information itself is used for other planets also. So of course you have to do some corrections for gravity of the planets, impact flux, in the solar system, and the potential for degradation in the presence of an atmosphere. So when there is an atmosphere, so then we have the problem, or the crater, this frequency distribution will have some issues actually. Like Venus has an atmosphere, Mars has an atmosphere, so it becomes problems, to find out. So there are some lot of, so these complex things are there. So people have tried to develop some type of algorithms and others, to handle these issues also. Okay. And now here the starting points to do this crater, to count the craters or to estimate the crater is basically, we can't go there, we cannot go there on Moon, and then you cannot count all of them. So our Mars or other planets, the only way is through remote sensing, or that is through images basically. Okay, so these are the starting points to count the craters itself. So the geomorphology, say most of our knowledge, the solar system of all planets is derived from remote sensing only. So remote sensing means it is just described as it is defined as collection of information, say, without coming into physical contact. That means we are not going there, just from here itself, sending an orbiter or something, getting an image, and then we are trying to get some type of information only. Of course, on Earth, remote sensing generally people do with the spacecraft, balloons and helicopters or robots they use, and then they do this one. So now the same things they have been done, are used to detect, specific parts, these electromagnetic spectrum people try to use, and then they use this electromagnetic wavelength, the temperature, infrared, so many issues are there. So they use these type of tools, and then they try to find out this the impact cratering and other details also. Now, generally, remote sensing, say, it is basically classified into passive or active. Okay, so passive means it uses natural radiation like sun and kind of a thing. Active systems, say, so they illuminate the surface with artificial energy source. See, like this is very important. If you are want to do on Venus or Mars, where you have a huge atmosphere, the rays may not penetrate. Okay, the sunlight and other things also. So they use an artificial energy source, a radar or something like that, and then use based on that, they will do this cratering, and they will try to find out the images of the planets itself. So radar imaging, so this is a active, remote sensing thing. So they will send radar imaging systems. It beams energy towards the surface, and some of which is reflected, and then it records by a radar sensor itself. So radar is essentially active remote sensing also. So this is what it happens. So two types people use. So this is the most important graph in remote sensing. So this is the electromagnetic spectrum. Okay. So based on the wavelength, right? Our human eyes say that is a visible portion. Okay. So our human eyes, we can see only the things say in this small band. Actually, in this wavelength only we can see. That is how our eyes have been made basically from the nature. Now, apart from this, we have other types of electromagnetic radiation, like for example, X-ray. I hope all of you would have taken X-ray, like the bone structure and other things also. Then we have gamma ray, which has very less wavelength basically, and then the cosmic ray radiation also. So these will have very low wavelengths, and the visible portion is here. And then if you see the infrared radiation, microwaves radiation, radios, these will have high wavelength kind of waves itself. Okay. So what this remote sensing, what they do is they use all these techniques actually. So they take images in cosmic, this infrared radiation, microwave this one, radio this one, so that they can find out the temperature and all the other things from the remote sensing itself. So these are the radar bands basically. Okay, so these are radio, whatever radio bands are there. So these are the wavelengths, frequency, and it also shows you where this has been used basically. Okay. So this is what, so nearly every spacecraft is say, whatever spacecraft we have sent in our solar system or even our Earth, so they have carried a image camera or imaging system, as a part of its a payload. Okay, it is a mandatory kind of thing. So they use this charge coupled devices. I have no idea, but this is what they use. CCDs as a detector rather than the film. So this is what they use. So CCD imaging systems, some lines or two-dimensional arrays they use. So these type of techniques they use, and then they take images, snapshots, and others. They try to do this one. So now images they produce single wavelength range, say as a black and white kind of thing are there, narrow, broadband. So many things are there. Then color images, so they are produced by obtaining the data for more than one wavelength actually. So they take several wavelengths, and then the color images also they try to frame. Okay, so many expose, like we know, right? I think visible means red, blue, and green. I think these are the three fundamental things our human eye can detect. So for that corresponding wavelength, say, so they get images for all corresponding wavelength, they superimpose, say, and then get some type of color images or something like that. Okay. So this is the most important thing. So the remote sensing, say, is a very fundamental in planetary science. So if we can do remote sensing, if we can get the images, we can count a number of craters or whatever things are there, and then we can infer this geological process itself. So the crustal structure of minerals, okay, they behave in characteristic ways when exposed to electromagnetic energy. So when you send variety of wavelengths, some minerals will behave in a different fashion. So based on that, they take images and then they do this analysis and others. So near infrared region also is there. Then multi-spectral spectrometers. So there's a lot of new instrumentations have come. Okay, so several things are there. Then or for example, see like for example this cosmic ray radio or gamma rays. Okay, so there are which aircraft there, which spacecraft they have done gamma ray radiation. Yeah. See, suppose Voyager 1 or Voyager, if you are going out of the interstellar space or whatever, so then you will see different types of radiations. Okay, so they decide what to use, what type of instrument has to be used also. So anyway, so this near infrared mapping spectrometer, I think it went on Galileo mission basically. Okay, so they have some because Jupiter also has a huge atmosphere, So if you have to penetrate it, if you want to see the surface, so you have to penetrate that one. So your wavelengths have to be very high. So a lot of instruments have been devised now. Okay, so there's what the disadvantage. So many methods have come. The spectrometer, mapping spectrometers have come. So many things like, and of course some surface materials, so they radiate energy, the heat will be there. Okay, by the radiation also happens, but our human eyes cannot detect. But electromagnetic spectrum say one can detect all these things also. Okay. So there's so many things. So thermal emission spectrometer basically. So this also has flown on Mars Global Surveyor say. It can measure the temperature itself, on the surface of Mars. Then so many things are there. Okay. So I think so much of instruments and then radars have come. Now that's what the radar, the most important thing is if you're having a dense atmosphere on a planet, say, like a Venus, Titan, of course, Mars also has, but Mars is not that dense. And if you want to understand so what is happening inside that planet, so we have to use this radar imaging. So that means its wavelength is very long, So radar, you can see through clouds also. And of course, this radar technology is also used in our aircrafts, when there is a huge turbulence or this one say, so that if flight can land, you can see through the clouds basically. So the same thing is used in the planetary things also. SAR, the synthetic aperture radar imaging system, they say. So these things have been used to study Venus, Titan, and then so many other things also. Okay. So these were the different parts of this one, and the radar has, it seems, some kind of a bands, radar band, X band, C band, and all these things have been developed from. Yeah. See the radar, whatever the technologies, thermal spectrometer, or all these things. Who developed all these techniques? These techniques were developed for what purpose initially? So the radar technique or these techniques they have been developed for initially.
War.
War, to detect like you followed, right? The X-ray spectrometer, all these things have been done for war. So if there is any vehicle is going, the heat differences they use, now also all the military things are using. The same thing has gone into space also. So that's what you see. So electromagnetic, if there is a gases, then ultraviolet part of the spectrum they use, X-ray spectrometers. So they use variety of instruments have come. But all the things, the basis is this figure. Okay. So which part of the spectrum you are, like you say, depending on the wavelength. So visible is here. So variety says there are instruments. So there is no single instrument which can have the complete thing. So some instruments operate in this region, like radio, radar here. Some instruments operate in this region. Some instruments operate in this region. Some instruments operate in this region. We don't have a single instrument. So variety instruments. So it depends. Like if you are sending it to Venus, say, then you may have to have a radar kind of a thing. If you are sending it to moon, say, moon doesn't have any atmosphere or there are no clouds, so you can that instrument may not be required. You can go to another instrument also. So this is the starting point for remote sensing, what you have to carry and other things also. Okay. So gamma rays has come, then gamma ray spectrometers, X-ray gamma ray spectrometers. I think they have sent in Apollo 15 and 16. So variety instruments have come into picture. And of course, the various techniques are all geophysical data. So like you see, the instruments have been designed, gravity, magnetic fields, to obtain from this also. Then topographic data. So this is also very important. Okay, the topography data. So they have been derived from the images or from the altimeters, say, that measures the distance from the spacecraft to the ground. And then Mars, this MOLA, this one came. Then lunar reconnaissance orbiter camera recently, that also has come. So they are used to make images, where illumination, direction, angle, and then you can control, and then you can get the complete topographical images itself. So radars, lasers, all these things have been used also. Okay, so they're providing. So this helps us, the gravity variations, the topographical variations on other planets and the surface features. So now in image processing also a lot of technological advances have happened. Of course, in your mobile itself, all of you are having, you see, variety of apps are there. You can increase the brightness, this, that the digital, this one, some DN, there's a digital number, So you can play with this, and then you can make it bright, or you can find out, and so many things have come. So like for example, say these are the same image, A, B, E, C, everything is same, A, B, C, D, E, looking at different portions. Like the histogram here, you can see, so it has been changed, like a stretched image, at DN levels, the digital number, if you change, you will get variety things are there. So like, for example, you can do filtering also. See, like a D. So D is basically a high pass filter you have done here. So differences in brightness are, so the image looks like this. Now C is low pass filter basically. So if you do low pass filtering, say, it looks like this, so variety of techniques have come. So DN, please remember this thing, digital number basically. Okay, so 0 means, is black, and DN 255 means it's a perfectly white level kind of thing they use. So you, by varying this one, say, you can get variety, the things you can get, from this itself. So then the calibrations also they do. I think sometimes images, so there are a lot of errors also will come. So one is called as a donut basically. So this is a very famous word they use in image processing. So what happens is the dust grains is they find their way into the imaging systems. So sometimes they may be in the dust may come up and it will come some kind of an artifact. So you can see here one dust grain due to that say it looks to you like a crater basically or some geological entity, but this type of things have come basically due to the dust on the camera or whatever, so these are also a big headache actually. I don't know how many of like on Mars, when the one photograph was taken long back, the digital that image shows that there is like a human face was there on the Mars, and then it was made in so many people reported that, but then there are something like the image processing some mistakes, so they will give this type of false informations also. Okay, so these are so many advancements have happened. So the stretching you can do to make it more DN levels. You all of you have download, if you have downloaded QGIS, say, so you can work on these images and you can do all these checkings, adjusting the DN level, what type of information it gives, any whether you can detect craters very nicely, which type of images, this one can just check it in this QGIS also. Okay. So now filters are also there. I think in QGIS you have the filtering also you can do, low pass filtering, high pass filtering, one can do also. So the DN values, that's what they say. Digital from the low pass filter are subtracted, from the image, leaving only the smaller variations in the scene, producing a somewhat sharper image. So this is the most sharper image basically. Okay. Now in low pass filter is this one. So it looks like this. So now which image is easy to detect craters? C, D, E among these three say, where you can easily detect the craters clearly.
So D.
Yeah, D you can count, right? The crater boundaries, you can see beautiful circles are there. Okay, so this is a big you followed the challenge in remote sensing. So how many craters are there? After look from the image, you have to tell us. Okay, so as already I told you, now I will send you some papers. People are using now machine learning also, deep learning methods to detect craters. See, like now, if you want to detect craters, say our human eye, we can easily detect like 1, 2, 3, 4, like that we can detect. Okay, but if you are doing on a planetary scale, say, you definitely, machine learning, it has, I think it has proved success also. And the images, whatever I showed you previously, all these craters, say, which I showed you in the starting slide. Okay. So all these craters have been detected by machine learning algorithm. You follow? So that machine learning algorithm, say, it also detects, the craters, how many number of craters are there. Yeah. So we use all these kinds of techniques itself to find the craters. So then geometric projections also. So sometimes, if you projection also matters a lot in what direction, stereographic projections, orthographic projections, so many projections are there. Like it depends, how the spacecraft has done inclination and other things also. So the geometric projection also becomes very, important in marketer projection. So many are there, stereographic projections also. And then mosaics basically. So what do you mean by mosaic? Yeah. Mosaics, this is a very famous word, right? Mosaic, when you are doing this image processing, it's very important. What is a mosaic? No. Yeah, mosaic means what?
Overlapping.
So what? You cannot take a single photograph of entire moon in one go. So what one does, you take a region photographs basically, and then what you have to do, you have to join them. So when you join them, say, so the multiple frames basically. Okay, so like you can see this figure. So here they have got so many images, one image here, one image here, one image. You can see slightly the border lines here. So these are all individual images basically. Okay, so now these individual images, these multiple frames, so you join them such that there will be no discontinuity and other things, so this is what we call this is a mosaics kind of thing we say. So mosaics, so they combine more than one image to matching pixels along the frame boundaries. So when you are matching this image and this image, so at this boundary you have to do that pixel matching and all other things have to be done. So that's what this mosaic, this is very important, because you cannot take image of moon in one go. So you will take region by region itself, and then you have to combine, and you should get a single map kind of thing itself. So these also mosaic things they do. So here also a lot of filtering, so many issues comes up. Okay, then of course there are so many processing techniques out there. Okay, so once the image is done, say, so they process it so nicely, and then so that it will convey any meaning, geological meaning itself. Okay, so a lot of, see, these are the cosmetic image processing techniques they say. So artifacts, you see the donuts, as I told you, right? The artificial dust on the camera, so many things they try to do itself. So you can see lunar photograph orbiters, say, strips of the film you followed. So that is in A. Then mosaic and image processing, results with smooth continuous image. Say. You can see how these images looks like, in each of these photographs also. So you can see you can see, right, some lines are there here in this image. Okay, so these lines have been removed basically. So they have several films are there. So now this is a processed one, B. So now after this image processing, say, now which one looks better, A or B? In A, what's the problem you are having? No.
These lines.
You can see, right, these type of lines. So sometimes, as already I told you, right, if you don't remove these lines, what will happen? No. So what did we say last class? Which crater is young? Which is the oldest region? So what did we say? That bright lines means young, like that. Also, there is some classifications are there. So if you don't remove this one, say, it may give you a false information. So much of techniques have come. If you have QGIS softwares, I think QGIS has all kinds of I think you can do all these kind of image processing, making the image looks much better. But one advantage is now already these things have been done. The lunar topography maps, which I think our Meenakshi has sent you in the WhatsApp group, I think all these images have been processed, and good high quality images only have been given to you. Okay. So resolution also matters a lot, the scale of pixels, what is the resolution. That also nowadays, I think 10 meter per pixel, now high resolution cameras have come. The older things had a large variation, but now very good, very high things also have come into picture. So resolution is very complicated kind of a thing we say, like 10 times, so many issues are there here also in the resolution. So you can see all these details, okay, in the remote sensing. And of course, electronic data records also are there, some level 0, level 1, level 2, level 3. So if you are doing in QGIS, you will understand these things in a better fashion. Okay, so like you see the original files, level 0, they say. That is, I think when you download the data set, even in NASA other websites also, they will give all these kinds of data sets. Level 0 means the raw data, whatever the original images, that's what. Then level 2 means they are decompressed. Okay, that's what they do. Then level 2 means they have all the calibrations they have done, and level 3 means they have all processed the data itself. So sometimes also 4 levels are there, I think. Okay, so unprocessed data like that, so many cosmetics and other things they try to do to get some meaningful, the information from these images also. Okay, so the cartography. So this is the most important. That is a maps basically. Okay, that is for exploration for all those things. So now generally, so the cartographic materials is say. So what is the geological age? I already showed you the geological map of India and other things also. So this also becomes very important, the cartography, the map preparation itself. Okay. So the topography images say. Now when it comes to topography, a lot of techniques are there. We will not go into the details, just you should know some of these names. Okay. Photogrammetry, photoclinometry, altimetry, so many techniques have been done. So like this is a digital elevation model. So these are topography data for that, Olympus moons. That is the largest, I think, tallest, or the huge volcano in our solar system. Okay, and it is on Mars. Okay, so these are very important, I think, the topography images and the digital elevation models. These are DEM images. Okay, so once you get this DEM set, you can construct the topography contours. You can do, or you can do that shaded relief maps basically, which will show the topography itself. So now the names for planetary objects and surface features. So now once you have gone to some planets, you take all the images, you process them, and then you make this one on the surface features basically. So we give some type of names and other things also happens. Okay, so they use this the names. How do they determine the age? Say, so a lot of things are there. So you can see there is some USGS, that gazette comes. So it is something like this. Okay, these are the names. Tessera or tesserae, they say. That means tile-like polygonal terrains. So when you see in the image, we call this as a tessera. Then tholus means in a small domical mountain or a hill. We call them as a tholus. Then valleys basically. So valleys means it is a huge valley. Like in Mars, we have Valles Mariners region, they say. So Valles means it is a valley. Then varga, so this means a streak or a stripe of color set. So they use these type of words to describe these surfaces. So these are the names they have given basically. Chashma, that means a deep, elongated, steep-sided depression. So this they call as a chashma. So in remote sensing, say, once you have all the images, you you will try to find out all these things itself. Like for example, say, oceanus. Okay, so oceanus means in a very large, dark area on the moon, basically. So this they call as the oceanus region. Then you have planitia, low plane, planum, say, plateau or high plane. We call this as a planum. Plume, cryovolcanic features. So these are the names which we regularly use. Like if you see that one paper I showed you right long back on Mars, cerebra fossae. They call them as cerebra fossae. So fossae, when they're using, say, that means it is basically a long, narrow depression itself. So that they call as fossae actually. Then they have a lapse. They say that means a landslide. Okay, so these are the names they use. Labyrinthus, so that means a complex of intersecting valleys or edges. They call this as labyrinthus kind of a thing. Then if you're having a small dark spots on Europa, so they call this as lenticula. So these are some of the names people have given based on this that in the website it is mentioned. So they use these type of names. So when you are reading the JGR Planets journals, say, so they give all these type of names, cerebra fossae, Valles Mariner. So these names will be there. So they have a specific meaning. Okay. So like fossae, as already I told you, right? It is some long, narrow depression. If it is a oceanus, say, a very large, dark area, so we call this as a oceanus, like that we call this one. And if you see a plateau or high plains, a planum. So these are very specific words. Okay. So I want all of you to just, if you go through this one, then you will be able to understand all the, like Maria. Okay. So Maria means, can you read this? So they said, right, Maria Imbrium on moon, they say. So what do you mean by Maria?
See,
See large circular plane and Titan. Then apart from that, large expansions of dark materials thought to be liquid hydrocarbons. So this we call as Maria. See on moon we said, right, Maria Imbrium. That so the Maria, so when they are using Maria, so that means this is the meaning, this one. Okay, so these words all have a specific meaning itself. So fine. So I will stop here. Okay. So we will continue in our next class. So what all of you have to do is of course in the next class what we will be doing is yes. Now, so what we will be doing in the next all of you have downloaded, right, this QGIS?
yes, sir.